Good morning, students. Today I am going to teach different types of hydrides and chemistry of water. This academic year, in chemistry of water, only physical and chemical properties are included. So I am going to teach covalent hydrides, metallic hydrides. These are the two different types of hydrides. And then I move to water and its properties. If time permits, chemistry of heavy water I will teach. And this is in continuation with the previous class. In the previous class, I was teaching ionic hydrides. Right? There, in ionic hydrides, time was up, so the class was dealing. One point was left out in that, that is lithium hydride. Means hydride of S block is used in making of other compounds. So in that, it was ionic hydrides. And in that ionic hydrides, S block metals form hydrides when they react with hydrogen. Right? Best example is lithium hydride. And these hydrides of S block are used in making of other compounds. Right? So these are used in making of other compounds. Now let us see which hydrides are used in making the other compounds. Best example for the ionic hydride, that is one which is formed with S block element. Means when hydrogen reacts with S block elements, we will get hydride. Best example for that is lithium hydride. When this is treated with Al2Cl6, this is dimer of aluminium chloride, Al2Cl6, or it can be written as 2AlCl3. So when these react with each other, it gives rise to lithium aluminium hydride plus lithium chloride. Here 6 chlorine atoms we have, here only 1. So multiplied by 6. Right? So altogether 8 lithium atoms. And here 8 hydrogen atoms. Automatically it's balanced. This is lithium aluminium hydride. This is the strongest reducing agent. Strongest reducing agent. This lithium aluminium hydride. So in that way, lithium hydride is used in making another important compound like lithium aluminium hydride. Now let us see one more example wherein lithium hydride is used in making of other reducing agent, important compound. When lithium hydride is treated with diborane B2H6, this is called diborane. Both will react with each other and give rise to lithium borohydride. And here we have 2 boron atoms, here only 1. So we will multiply whole thing with 2. So 2 lithium atoms, here 2. Now hydrogen atoms we have 8, 2 plus 6, here 8. So it's balanced. The name of this compound is lithium borohydride. So that's about the balance part of ionic compounds. Now, today's first type of hydride is covalent hydride. In the order of hydrides, this is the second one, and in this class, this is first hydride. Okay, that is covalent hydrides. So, hydrides means those compounds which are resulted when hydrogen combined with elements of specific groups, like first group, 13th group, 14th group, right? 16th group, 17th group, and so on. That and all we will see as and when concern concept comes. Now let us see covalent hydrides first. Covalent hydrides. The name itself is informative. In chemistry, covalent means one which is formed by sharing of electrons. So covalent hydrides means those hydrides which are resulted when hydrogen shares electrons with the concerned atoms of the different elements. So they are covalent hydrides. Next, among covalent hydrides, some hydrides allow electricity to pass through them. Some hydrides do not allow electricity to pass through them. Example, water. It is covalent hydride. Right? It allows electricity to pass through it. Glucose, if we take, it is covalent compound, covalent hydride, because hydrogen has combined with the carbon there. Of course, oxygen is also there. And there are some compounds which do not allow electricity to pass through them. Fine. And in these covalent hydrides, we have varieties, means different types. Whether these covalent hydrides have required number of electrons for the formation of bonds or not. 1 point. Number 2. Whether these covalent hydrides have deficiency of electrons in their molecular levels. Next, whether these covalent hydrides have more than the required number of electrons. So based on these, we have 3 varieties of covalent hydrides. What are those 3? Let us see. First one in this is electron deficient hydrides. Electron deficient hydrides means these hydrides do not contain required number of electrons, or they have shortage of electrons. So such hydrides are known as electron deficient hydrides. Best example for this type of hydrides is diborane. Example for this is diborane. Its composition is B2H6, which contains less number of electrons than required. Next, usually this type of hydrides are formed when hydrogen combines with 15th group elements. This is second important point. So form when hydrogen combines with fifteenth group elements. Fine. Now we'll move to second type of hydrides, that is electron precise hydrides. Precise means in chemistry required, right? So how many electrons are required for the formation of hydrides? If exact number of, there should not be more, there should not be less. So what exactly required? That number of electrons, if it exists, it can be for the formation of bonds. Then that is said to be electron precise hydride. So second type is electron precise hydrides. So these hydrides, first point, these hydrides contain, or these hydrides have a required number of electrons. In them. And second point, usually these hydrides are formed when 16th group elements combine with hydrogen. Okay. So second point is formed when hydrogen combines with 16th group elements. Here this is 14th group and 16th group is oxygen, carbon, 14th group elements. And best example for this is methane. That is CH4. So around carbon we have 4 bonds. For 4 bonds 8 electrons are required. So 8 electrons are there. So methane is said to be the electron precise hydride. If you take diborane, right? So there we have shortage of electrons. So that is electron deficient hydride. Now we are moving to third type of hydride, that is electron rich hydride. So electron rich hydride means those hydrides which contain more electrons in them, means more than required. So how many electrons are exactly required for the formation of bonds? More than that number of electrons, if they are there in that hydride, then that is said to be electron rich hydride. So we can write these hydrides have more than required number of electrons. Next, second important point is These hydrides are formed when 17th group elements combined with hydrogen. 17th group elements means chlorine, bromine, etc. And also 16th group elements. 16th group elements means oxygen, sulfur, etc. So here second point we can write formed when hydrogen combines with 16th, 17th group elements. Example for 16th group element is oxygen. So here we can take hydride of oxygen, that is H2O. This is dihydrogen oxide, that is chemical name of water. So wherein oxygen belongs to 16th group and it has two lone pair of electrons. So it is electron rich compound. And other example is hydrogen chloride. And here chlorine belongs to 17th group. Right? So atomic number of chlorine is 17. Means outermost shell. You recall the electronic configuration 1s2, 2s2, 2p6. 10 electrons over. 2s2, 2p5. Means 7 electrons are there in the outermost shell. Out of those 7, here 1 is taking part in the bond formation. And remaining 6 electrons will be there around chlorine. So it is electron rich species. In that way we can take 15th group element, right? That is nitrogen. And hydride of nitrogen is nitrogen trihydride, that is ammonia gas, NH3, where nitrogen has one lone pair of electrons. So these are examples for the electron rich hydrides. Now we will move to third type of hydride, that is metallic hydride. These are also known as, these metallic hydrides are also known as non-stoichiometric hydrides. The other name given to these hydrides is non-stoichiometric hydride. This is the other name given. Now let us see first what are called metallic hydrides. So those hydrides, when they are formed by the combination of the metals of D block, F block with hydrogen, then they result metallic hydrides. And usually in these metallic hydrides, right, there are number of pores. Transition elements contain number of pores into which hydrogen gas can be incorporated. That is why these hydrides are also known as interstitial hydrides. Interstitial hydrides. In chemistry, interstitials, holes, cages, pores means same. Now, in the case of these metallic hydrides, as I told you, when the metals are D block and some elements of F block, when they combine chemically with hydrogen, these hydrides are resulted. And these D block elements contain number of pores in them, P-O-R-E-S, means holes, or interstices, means on the surface of these D block elements or transition elements we can see number of holes, and hydrogen gas will be incorporated in those holes, and then in the inner wall of those pores these hydrogen particles will react chemically to form what you call metallic hydrides. Since pores are there on the surface of the metals into which these hydrogen particles entered and reacted chemically, so they are known as interstitial hydrides. Right? Now let us see what are called non-stoichiometric hydrides. Non-stoichiometric hydrides. Now look at this compound, that is zirconium hydride. This is one compound, right? It is zirconium. Many compounds are there. I have taken one example to convince you to understand what are called non-stoichiometric hydrides. Now, ZrH, this molecular formula shows that when 1 mole of zirconium reacts with 1 mole of hydrogen atoms, then we will get zirconium hydride. So ratio of zirconium, right, its atomic number is 40, and hydrogen is 1:1. Right, that is what stoichiometry of this zirconium hydride speaks about. Stoichiometry refers to the number of particles or number of atoms present in one molecule of the compound. Here zirconium hydride is compound. In this we have one atom of zirconium and one atom of hydrogen. But it was found that in zirconium hydride, ratio of zirconium and hydrogen particles will not be equal to 1:1. So it was found that zirconium is 1.3 atom, hydrogen is 1.75 atom. Means here this ratio 1.3 and 1.75 is not equal to 1:1 ratio as per the stoichiometry. Right? This is quite opposite to a stoichiometry. Therefore, this compound is said to be non-stoichiometric compound. That is non-stoichiometric hydride. So non-stoichiometric hydride is one wherein the real or the actual ratio of different atoms of the elements present in it are not equal to the molecular formula of the compound, how it apparently looks like. That is the reason why these metallic hydrides are also known as non-stoichiometric hydrides. So that's about chemistry of hydrides. Now, let me move to the other part, that is the other topic, today's second topic, that is water and its properties. First, let us see what is meant by water. Water is nothing but a solvent which is capable of dissolving many different types of substances in it. In this planet, this is what we call unique solvent which is capable of dissolving many different types of compounds in it. That's why it is said to be universal solvent. Right? Number 2. Chemical formula of water is H2O. So, chemical name of water is dihydrogen oxide. So, chemical name is dihydrogen oxide. If water doesn't exist, then plants cannot exist, animals cannot exist. Since we are heterotrophs, we are not autotrophs, we are depending on plants for food. When plants cannot exist, then we too cannot exist. That means, if water is not there, then we cannot exist. Plants cannot exist, animals cannot exist. That way water plays vital role in biosphere. Next, this session, as I told you already, much information about water is deleted. Directly, physical properties and chemical properties are included. Now let us see what are the physical properties of water. As far as physical properties are concerned, number 1, water doesn't have any color and it exists in liquid form. So, we can write it is colorless, liquid substance. Number 2, it dissolves many substances in it by forming hydrogen bond. At the same time, if you take water alone, it has uncountable H2O molecules, and all these molecules are joined to each other by means of hydrogen bonds. This joining process is called association. So, water exhibits association by hydrogen bonds with its H2O molecules. Now, Third physical property. Water has high boiling point, 100 degrees centigrade, and water has high heat of vaporization than hydrogen sulfide H2S, hydrogen selenide H2SE. So this is other property. So why water is compared with hydrogen sulfide and hydrogen selenide? So water is H2O, hydrogen sulfide is H2S, hydrogen selenide is H2SE. So this property specifically why it is compared with H2S and H2SE, that is hydrogen selenide, is like oxygen, sulfur and selenium belongs to same group, that is 16th group. That is the reason why specifically these two properties, that is boiling point and heat of vaporization, are compared with dihydrogen sulfide or hydrogen sulfide, hydrogen selenide. So this property can be written in this way. Hope reason you could have understood why H2O is compared with H2S and H2SE. So it has high boiling point and heat of vaporization than hydrogen sulfide and hydrogen selenide. SE stands for selenium. H2SE, hydrogen selenide. Okay, now fourth property. It has high dipole moment and specific heat, etc. Next, it dissolves many compounds in it like alcohol, carboxylic acid, etc. by forming hydrogen bond with them. That means those compounds which are capable of forming hydrogen bond with water are said to be miscible or soluble with water. So it can be written, it dissolves many compounds by forming hydrogen bond with them. Examples: alcohol, ROH, and then RCOOH. RCOOH stands for carboxylic acid. So these are the physical properties of water. Yes, children. Now we will move to chemical properties. Water exhibits different chemical properties, like number 1, amphoteric property. So amphoteric substance means a substance which behaves like acid as well as like base is known as amphoteric acid. Here water behaves like acid, it behaves like base, and in our body it behaves like neutral substance. Now let us see where it is going to behave like acid as well as base. So H2O here, this acts as acid. Right? When it reacts with NH3, with ammonia gas, right? It behaves as acid. So according to one of the concepts, acid is nothing but a substance which is capable of donating proton. So when it donates one proton to NH3, it will become NH4 ion, that is ammonium ion in aqueous form. After donating proton, it becomes hydroxyl ion in aqueous form, and this is a reversible reaction, right? So here NH3 is base. Now let us see the other example where water is going to act as base. So that means there must be such a substance which acts as acid with water. That is hydrogen sulfide. It is gaseous substance. This acts as acid. Right? When these two react with each other, we will get hydronium ion in aqueous form and HS minus ion. Hydrogen sulfide mononegative ion. And here H2O is said to be base because it is capable of accepting proton now. So proton acceptor is base. After accepting proton from hydrogen sulfide, it has become hydronium ion. This is one property, that is amphoteric property. Next, redox nature of water. Redox reaction means a reaction wherein oxidation and reduction are taking place simultaneously. That is said to be redox reaction. Here, best example for the other substance. Since we are discussing about chemical properties of water, so water is the main reactant. The other substance is sodium metal. It is highly reactive metal. So when water is treated with sodium metal, we will get sodium hydroxide plus H2 gas. Right? So 2 sodium atoms, 2 H2, oxygen, 2 atoms and 4. Yeah, it is balanced. Right? In this case, hydrogen has positive charge, whereas here in H2, hydrogen has 0 charge. Means positive to 0. When oxidation number changes from positive to 0, that will see little later what it should be called as. Now let us see sodium and sodium hydroxide. Here in this compound, sodium has positive charge and here sodium has 0 charge. So all elements in their atomic form will have 0 as their oxidation numbers. Right? Now sodium to Na plus ion means 0 to plus means increase. 0 to plus increase means increase in oxidation number, and that is called oxidation. And in this case, that is H plus to H0, plus to 0 is decrease in oxidation number. So this is called reduction reaction. So in this reaction, both oxidation and reduction are taking place. Therefore, we call this reaction as redox reaction. Now, last but one reaction, that is hydrolysis. Means reaction with water. What is going to react with water? Let us see. First example is phosphorus pentoxide. When it reacts with water, it gives rise to inorganic acid containing phosphorus. That is phosphoric acid, H3PO4. So the reactant is H2O and it is reacting with P2O5, phosphorus pentoxide. As a result, we will get phosphoric acid, H3PO4. Here phosphorus 2 atoms, here we have only 1 atom, so multiplied by 2. Now oxygen atoms, here 8, here we have 5, means 3 more required. So this is multiplied by 3. 6 hydrogen atoms and 2 phosphorus atoms. Yeah, it is balanced. P2O5 is phosphorus pentoxide. And the last chemical property. Here, one more example is given in your NCERT book, that is nitride. After that, we will move to the last chemical property. When nitride radical, any substance which is capable of donating nitrogen in the form of anion, its oxidation number is -3. So we write 10 -3. So when this reacts with water, right, and it gives rise to NS3 and then hydroxyl ion, 4 hydrogen atoms. Here we have only 2 multiplied by 2. 3, 4. Now 2 oxygen atoms. And 5 it has become. Let me write here 3. It will become even number. You see with that and here. 3. 3 by 1. Yeah. Now the last chemical property is capacity to form coordination compounds. Formation of coordination compounds. Water is able to form coordination compounds. How it is going to form coordination compounds? Let us see. Coordination compound will have coordination sphere in it. Already I gave in the previous sessions how it looks like. If we take its composition, right, its formula will have square bracket, that is called coordination sphere. Right? In that coordination sphere or outside the coordination sphere there can be water molecules. Means crystals can be made or converted in such a way that they can get water of crystallization in them. Example for this is hexachromium 3 chloride. Its name is hexachromium 3 chloride. This is called coordination compound wherein water molecules are incorporated in them. Thank you, children.